Very good morning to all. It is our great pleasure to welcome you all for the 1 week FDP on purely the fundamentals of mechanical engineering. This 1 week FDP is conducted through the initiative of Chennai Technology on Knowledge 4.0 webinar series, which is one of the unique initiative under the guidance of our Honorable Chairman, Sri P. Sriram, who is one of the well-known, successful first-generation entrepreneur, managing director of MK Group of Companies. Under Knowledge 4.0 webinar series, we have been conducting webinar series such as Technical Webinar Series, Research Webinar Series, Innovative Talk Webinar Series, and Career Guidance Webinar Series. Along with this, we are also conducting international seminars, national conferences, international conferences, and faculty development programs. These programs are being conducted only to enhance the knowledge of faculty, researchers, and students community as a social responsibility. So today we have Dr.K.Jayabal, professor from IIITDM Kanchipuram, to give an expert lecture on the fundamentals of engineering mechanics. Let me welcome you for this wonderful session, sir.
Yeah, thank you for giving me the opportunity.
And Chennai Technology was started in the year 2010 by our Honorable Chairman Sri P. Sriram, and today our institute is being within top 10 among all other private engineering colleges in Tamil Nadu. It is my great pleasure and honor to welcome you all the participants and today experiment Dr. Jayabal sir. And now I request Ms. Supna Sri to introduce our experiment member.
Good morning, everyone. Myself, Swapna Sai, pursuing second year mechanical engineering in Chennai Institute of Technology. Today is our expert, Dr. K.Jayabal, sir. Dr. K.Jayabal is an associate professor, Department of Mechanical Engineering, Indian Institute of Information Technology, Design and Manufacturing, Kanchipuram. He did his BE in Mechanical Engineering from Government College of Technology, Coimbatore, in the year 1994. And ME in CAD from University of Madras in the year 1999. He received his PhD in Applied Mechanics from IIT Madras in the year 2009. In 2012, he also received postdoctoral fellow in material modeling from Technical University Dortmund. He specialized in finite element methods and material modeling. His areas of research includes finite element methods, smart materials and structures, biomechanics, thermoelectric devices, mechanics of materials, engineering design. He has over 20 years of experience in teaching as well as in research. He was awarded as
Swapna, thank you, Ms. Swapna, thank you very much. Since I started late now, that means not from my side. Due to technical issues, I had to start late. Okay, thank you for your kind words. Okay, because yeah, they can directly we can get into the presentation. Okay, sorry for interrupting you, Swapna. Thank you, but you have given enough information about me. Thank you very much. Okay. Yeah, thank you, Swapna. Professor, we can directly get into the to save time because we are running. Yes, yeah. Very good morning to all of you. I think the participants includes a mixture of people. So at any point of time during the presentation, if you want to get your doubts clarified or any queries, no, please stop me in between. Don't hesitate to stop me, and then you can raise your queries. I'll be happy to address you. And what I do is I'm going to turn off the video so that the data transfer will be less. Okay. So at any point of time, if I'm not audible also, please don't hesitate to interrupt by some means. Today's topic given is engineering mechanics. So I think some of you might be familiar, well versed in that, and some of you may be in the process of learning the subject. So engineering mechanics is a very fundamental subject. As you know that several people have laid the foundation even before Sir Isaac Newton, Archimedes, and so many great people have contributed to this. So this engineering mechanics is fundamental for almost all the scientific advancements from the mechanical engineering perspective. For example, as you see here, these structures, and even the moving objects, space explorations, everywhere we are using the engineering mechanics principle only. So the slide is prepared based on the input available from Vector Mechanics for Engineers by Beer and Johnson primarily. And then this engineering mechanics consists of two parts like statics and dynamics. And actually, this engineering mechanics is to be taught in 40 hours. So statics should be taught in 20 hours approximately, and the dynamics part should be taught in remaining 20 hours. Since 1.5 hours is the time allotted to us, what we are going to do is we are going to see only the statics part. That also we are going to see the fundamentals and solve one or two problems based on that concept. So as I repeatedly say that you don't hesitate to interrupt me at any point of time, or after completing a particular session, I will be asking you if there is any query. You can ask your raise your queries. And then some fundamentals related to engineering mechanics is like we know a force, it is a vector, and a couple is also a vector. Frequently we will be dealing with the equivalent couple in the engineering mechanics. So for example, here we know what is a couple because that is the like when two forces which are having the same magnitude, opposite sense, and they are separated by certain distance, then they will form a couple. So this couple can be replaced by another set of forces separated by different distance, but they will be producing the same effect. They are called the equivalent couple, and frequently we will be introducing this equivalent couple. So as you see here, these two forces which are 20 pounds separated by 6 inches. So when the couple generated by this system is 6 into 20, so 120 pounds each. But this can be replaced because this is going to make this box to rotate in the counterclockwise direction when we view from the top. Otherwise the m direction is the moment vector direction. So instead of this we can use another set of forces, say 30 pounds separated by 4 inches, so it will be again 120 pounds per inch, but that will also produce the same magnitude. That means with the same magnitude it is going to rotate and in the same direction counterclockwise. That's why the moment direction is, the coupled direction is in the upward direction. That holds good here also. So frequently we'll be using, that's why. And then in engineering mechanics, the fundamental question would be whether we have to treat the body of interest as a particle or a rigid body. Actually, we can always treat that as a rigid body. So if you are doubtful about whether we have to treat it as a particle or a rigid body, don't hesitate, go to a rigid body, because that way you are not going to lose any important point. But when we are taking it as a particle, we have to be careful, because if there is any rotation associated with it, then we cannot take it as a particle. It should be as a rigid body only. For instance, when we take sun and moon, we are going to deal with only the gravitational attraction between these two objects, then we can treat them as a particle. But when we are taking the moment, angular momentum or other aspects, rotation of Earth, that time we have to treat the same Earth as a rigid body which was treated as a particle earlier. So depending upon the problem, the same body can be treated as a particle or a rigid body. So that is an important point. And then here, for example, the same example is taken, but we are going to see what is a free body diagram. Another important aspect in the engineering mechanics is, or the foremost important point is the free body diagrams. So when we are dealing with the system, we may be interested in on a particular object. So we have to separate that body of interest from the surrounding, and then we have to replace the constraint applied by the surrounding body by forces. For example, here as you see, this car is actually lifted up. It should be exported, so it is being lifted up with the help of the crane. This is the total picture shown to us. What we are interested in is to find out how much force this person should be applying through the rope. So for that, what we have to do is we are interested in finding the force that should be applied by this person along the rope AC. So for that, what we do, we have to take the point A, the knot at where three ropes are coming and joining them. So we have to take that point A as a particle as indicated here, and then we try to solve. So here we are taking the point A as a particle, and then we are replacing this rope AC by a force. So it is called a tension AC, and then weight of the car which is acting vertical. So there is 3,500 pounds which is acting in the downward direction, and the force acting along the rope AB, which makes an angle of 2 degrees. So FAB, otherwise tension AB is acting here. So from this, what we understand is we have to be very careful, because we may gain the knowledge, necessary knowledge in the engineering mechanics, but over a period of time, after gaining the experience only, we will be knowing how to separate a body of interest from the surrounding, and whether to treat it as a particle or a rigid body, and then proceed. So free body diagram is very, very important. Okay, so for example, another object is given here, but in the previous case, here we treated this point as a particle, whereas in the next slide we are taking this as a rigid body. Okay, so this block A, B, this block is going to be treated as a rigid body, because you see the forces are acting at different points. For example, the rope CE is attached at point E. Swapna, are you able to see the movement of the cursor here? Hello? I do not know whether is there anyone who can respond that you are able to see the cursor movement? Either you can respond by chat, or
Excuse me, sir.
yeah,
Not able to see, sir.
you are not able to see the cursor movement.
No, sir. No, sir.
Okay, so should I make it as a full screen? Then you would be able to see that, or is there any option for that? Oh, there is a. Okay.
Not able to see now also, sir.
Now, no.
No, sir. No, sir.
Okay, this is whiteboard, and then is there any option here to just any torch, like in a Zoom or Google Meet? There are options, like to show the like where I'm pointing. No, is that possible here
I
in this
think you
webinar?
can do the right click on the PPT and you can change pointer. You take it out, sir.
It's not coming. The settings button, chat, polls, offers, videos, files, slides, and hand signal is there, but no, surprisingly. Okay, turn whiteboard on. Probably now will it be possible?
No, sir. Not able to see.
Sir, hello.
சொல்லுங்க sir.
So, yeah, we are able to see, sir. You can go on. Now it's okay.
You are able to see the cursor?
Cursor, we are unable. Cursor, we are free body diagrams is able to see, but cursor is not visible, sir. Cursor, we are unable to see.
Okay, sir. Okay, because that will be fine in case of the other webinars, no, so that I can point directly, but you will have to follow them.
So
okay.
for that, the option will be when you share your screen, it will be possible. Now for this, it's not possible. So what we can do, sir? So, can you share the screen?
Yeah, I can share it, sir. So how to do that here?
Yeah, please, sir. Please. Now I come out from the presentation. So now you do one thing, sir.
Yes, sir.
From the top where you have turn off on your video, you will find the third position as a computer.
Turn screen on. Yeah,
Yeah,
fine.
please make it. And
Select
as soon
window
as
or screen.
you select entire screen, sir, entire screen.
Yes, entire screen.
Now share, sir. Share.
Okay.
Yes, sir. Good, sir. Good, sir. Good, sir.
Now you
Good,
are
sir.
able
Yes.
to see me?
Yes, sir. Pakka, sir. You can go
Okay.
on, sir.
Okay, sir. Now you are able to see the cursor movement.
Yeah, we are able to see cursor.
Yeah,
Sir.
that's what I want to happen. Okay, sir.
Please, sir, please.
So here we are taking this as a thank you, Professor. Yeah. And here we are seeing this as a rigid body. And this rigid body, now you would have figured it out already that when we have to treat as a particle, when we have to treat it as a rigid body, because here at three different points the forces are acting. At point E towards EA, and at point B towards BD, and at the support A. So forces are acting. So now here we are taking it as a rigid body. But you can understand if the entire block is supported by a single rope such that it is passing through the center of gravity, that time you can conveniently treat the same slab as a particle. So I believe that you would figure it out the difference between them. So while drawing the free body diagram, we must know what are the reactions coming from the support and the adjacent body which is applying force. So in the reaction, it could be either in the force form or in the moment form. For 2D, some support reactions are shown. For example, the rollers. It doesn't matter which type of roller or rocker or a rod which is moving on a frictionless surface means the reaction will be only upward direction. From the surface, it will be perpendicular and it is acting in the upward direction. And here, the direction of the force is known, but the magnitude is unknown. We can find out. So, in other words, one unknown. In case of a short cable or a short link, here also only one force will be acting along the cable or along the link whose direction is known, but the magnitude is unknown, which we will be finding it out. Similarly, the reactions at supports 2D of other types. For example, this is interesting. Here you have a collar. This collar is sliding over another rod, and this collar is attached with the link. Now we want to draw the free body diagram of this link. Okay, so that means we are going to remove this collar and the rod. The reaction from the collar is to be applied. That time you see that it should be perpendicular to the rod along which it is sliding. Similarly, here also you can see that when a force is applied, this force will not be applied along the line of this one, unlike the previous case. But here, the reaction force will be perpendicular to this one. We may wonder why. For example, here in this case, a force is applied in the same direction. What would happen? It will be resolved. If a force is acting like this, it should be resolved into two components. One is along the axis of this rod and perpendicular to the axis of the rod. Along the axis of the rod will be making the color to move along this direction. So if there is any force acting along the axis, it will be allowing the color to move there in the direction. That's why the reaction will be only perpendicular direction. That is what you see. Similarly, for a frictionless pin or hinge, it will be two components, horizontal direction and vertical direction. Otherwise, you can take it as a resultant also. So, if it is a horizontal vertical component, you have two unknowns. If you have a resultant also, two unknowns, but the unknown will be in terms of magnitude and in terms of angle. So, for rough surface or frictionless pin or hinge, we will be having two unknowns as indicated here. Sometimes we have the fixed support also. That time, in addition to the horizontal vertical forces, there will be a couple also. So these are the reactions from the 2D. Reactions from the 3D is shown here. So there is a ball, and then which is attached at the end of the rod, and here the reaction will be only in the upward direction, or it could be downward direction also, depending upon how it is actually the force is applied. But what we can understand is the line of action will be perpendicular to the surface, but it is free to move along x-axis, along y-axis. That's why whenever the object is allowed to move freely in a particular direction, if there is no constraint, then there will not be any reaction force in that direction. So that way, so it is not having reaction along x-axis, along y-axis, but there is a reaction in the vertical direction because the ball cannot penetrate and go below. Similarly, for frictionless surface also same reaction because there is no friction. In case of a cable, then here the line of action will be acting along the length of the cable. So along the axis of the cable. So see, the line of action is known, the magnitude is unknown, which we can find out. Another interesting support is this one. See, here we have a roller and it is on a rough surface. So what will be the reaction for this roller support is, as usual, we are very sure that there will be a vertical reaction force which is shown here. Okay, here they have taken it as y. So vertical direction is y. So Fy reaction will be there. But what about the other two directions? This is x-axis and this is z-axis. So it is a roller. It is a rough surface. It can move horizontally and it can slide along the z-axis. So this is x-axis. Along the x-axis it can roll. Along the z-axis it can slide. So definitely there will be some amount of rolling resistance, but for practical purpose we can assume that the sliding friction is much more than that of the rolling friction. So if we want, then we can neglect the rolling friction and then we can take the sliding friction alone. That's why only two reaction forces are indicated. But sometimes the rolling resistance will also be having higher value. It is very similar to our car or bike. If the tire is not inflated properly, even the rolling resistance will be more. That time, if it is considerable, then you will have to introduce the reaction force in the x-axis also. That's why we have to see that depending upon the problem, we will have to neglect or account the reaction forces. But here it is very clear because the vertical force is acting in the upward direction. It can move along this direction, so the rolling resistance is neglected. But here you see that it cannot come out in the z direction. That's why you are having the z axis. And in case of a ball and socket, you know that this cannot be moved along x, y, z direction. That's why three reaction forces are there. But you are free to rotate. That is the beauty of the. It is like a joystick. You can rotate about x axis, you can rotate about y-axis or x-axis or z-axis. That's why there is no reaction force. On the other hand, if we take a 3D support, then what happens is, you see that uh, in addition to x, y, z, you cannot rotate about three axes, so the reaction will be coming from the three directions also. That means if you try to rotate in this direction, the support will not allow. Or you want to rotate in this direction, it will not rotate. Or if you try to rotate about its own axis also, it will not rotate. That means the support will be offering resistance for the three rotations also. That's why we have the reactions mx, my, mz. So in addition to Fx, Fy, Fz, three reaction forces, we have the three reaction couples also. So this is the maximum possible reactions provided by a support, that is 3D fixed support. And depending upon the need and the convenience, we will be transforming a 3D problem into a 2D problem. Sometimes 2D to 1D problem. So most of the problems will be solved by 2D and sometimes it will be 3D also. Why we want to reduce from 3D to 2D means we will be losing some, of course, some like the exact results. It may be slightly deviating, but depending upon the computational cost, we decide that okay, we can live with short loss of the accuracy. So accordingly, the reactions also we change. And then one important theorem in the engineering mechanics is Vergnon's theorem, and this is for concurrent forces. You know what is a concurrent force? Concurrent force means all the forces will be acting at a particular point. It may not be exactly acting at the point, but if we extend the line of action of that force, then all the line of action of the forces must be passing through a single point. Then we call it as a concurrent force. If it is a 2D system, then 2D concurrent forces. If it happens in the space, then it is a 3D concurrent force system, right? And here such a 3D concurrent force system is shown, or 2D also doesn't matter. Then what we do, we are going to see that all the four forces are passing through point A, and this point A is located a distance r from the origin. Here you are free to fix the coordinate axis at your convenient place. Need not be here, it can be anywhere. And then if you find out the uh, moment produced by the individual forces, for example F4 times R, but in vector form it is R cross F4. The moment to produce by force F3 will be R cross F3. We should not do the reverse because it is a cross product. You know that. So cross product we cannot reverse it. Only in the same way we have to take. So R cross F2, R cross F1. These are the moments produced by individual forces. Now if we sum them up, then we will get the total moment produced by these individual forces. That is equal to, directly find the resultant of all these four forces, which is resultant say R, capital R. Then the moment produced by that resultant force will be equal to the sum of the moments produced by the individual forces. That is called the Vergnon's theorem, which is often used in the analysis. Now let us take two problems, like equilibrium problems, so that we can apply the concept. Here we see a practical application is shown here. There is a tower which is held in its place with three guy wires. Okay, these cables are which are called as guy wires for practical purposes, and AB, AC, AD. These are the three guy wires which are keeping this tower in its place. So in several places you would have noticed even the transformers, no, the high power transmission towers are supported in its place with the help of these three towers, so that even if there is a cyclone or a heavy wind, still they are capable of withstanding that load. Now, as a design engineer, you will have to find out what is the force acting in these cables. So why should I know the force acting in the cables? That is the next question we ask ourselves. Because you have to find out what is the diameter of the cable, because it will be a rope like wire cables. So what should be the diameter and what should be the material to be used? Because if you go to the market, there will be several wires. So you will see that how much load that wire will be capable of. Under each category they would have mentioned it, graded. Now if you know what is the force that is going to act on the cable, now you can decide which cable you have to use. If you are going to take a lower graded cable, that means which is not going to withstand this load going to come up here, then what will happen, it is going to break, if the system will collapse. If you are going to take a much higher one, then definitely you are investing uh, money unnecessarily. Several cables you are going to buy, it will incur huge loss to the company. So as a mechanical engineer, you should know what is the force acting here. For that you are going to use the mechanics, and then here you are going to use the equilibrium equations. For example, here a transmission tower is held by three guy wires attached to a pin at A and anchored by bolts B, C, D. So there are three bolts B, C, D. In this also you would have noticed the very huge bolts will be attached in the concrete slab. If the tension in the wire AC is 920 lb pounds, but actually in the SI unit it is going to be in terms of Newton or kilonewtons or tons, you know that. So here determine the vertical force be exerted by the tower on the pin at A. So how much force will be acting at the pin? That is the question, or the question could have been what is the force that is going to be acting along AC and acting along AD, because depending upon the space available, these slabs will not be exactly equally distributed at equidistance, because you see that in the city and all they will make that tower, that time depending upon the space availability only they will be making the concrete foundation. So accordingly, the cable, different cables could be used. In some cable may be requiring higher force, then for that particular cable alone, you have to go for a higher grade. So you have to find out. So using the equilibrium equations, you take point A as a particle, and then if you take this as a particle, three forces are acting in the downward direction along the cable AD, AC, AB, and at A from OA it will be a vertically upward force. So it is a four force. It is actually four force system, but they are going to be in equilibrium. This is a 3D problem. Since it is a particle, we will have three equations. So we have to remember, if a particle is in equilibrium and it is in a three-dimensional problem, that means the forces are acting like AB, AD, AC. They are acting in three-dimensional space, but it is a concurrent force, 3D concurrent force system. So we can have three equations: sigma fx equal to 0, sigma fy equal to 0, sigma fz equal to 0. You know how to resolve these forces. Finally, you will be able to find out three unknowns, because three equations are here now. So one of the force in the cable is known. So the three other forces, AC, AD, and then OA, we can find out. So now I'm sure that you would have got some idea how to solve a problem. This is a particle problem, three-dimensional concurrent force system. Here again it is a particle. Here you can see there is a slab and a weight is attached with by two cables AB and AC, and another force P is acting. Now we want to find out the weight is given. It is used in many signboards. You would have seen that in several places we will be using the cable or some link, rigid links, to hold the hoardings. So you should be able to find out how much, what should be the like a cross section of the particular supporting member. This is also a particle three-dimensional concurrent force system. So let us see the same problem that we have seen few slides before. Here this is another, you can say this as a signboard, or like from here Delhi some kilometers, thousands of kilometers, or some advertisement. There we have to find out what should be the cable, what type of cable, how much force will be acting. And here if you want to use a hinge, then what type of hinge we have to use, what should be the force acting at the support. For that we are going to use, here it is a rigid body, and then it is a three-dimensional rigid body, but not a concurrent force system. This is a non-concurrent force system. Why? Because the force BD, FBD, FEC are not acting along the same line. If you extend, they will be passing through the some point. But what about the force, which is the weight of this slab, which is going to act at its center of gravity, and the three reaction forces will be acting at the support A, because it's a hinge. So Fx, Rx, Ry, Rz, three reaction forces will be there. So we will have to treat this as a three-dimensional non-concurrent force system. For three-dimensional non-concurrent force system, the equilibrium equations available for us is sigma fx 0, sigma fy 0, sigma fz 0, and sigma mx 0, sigma my 0, sigma mez 0. As we have seen few slides before, we will have six equations. So it is obvious that we can solve as many as six unknowns from this problem, and we can find out the reaction, the tension in the cable, and also the reactions at A, provided we know the weight of the slab. Thereafter, once you know the force, then in the strength of materials course, you will be learning what should be the diameter and what type of material we have to use, so that we can fix the type of material and the cross section here, and the support also. So with this we complete the equilibrium of particles and equilibrium of rigid bodies. Here, quickly to summarize what we have seen now, we have seen what is a particle, what is a rigid body, and how to transfer a force into a force coupled system or equivalent couples, and then how to solve a particle problem and how to solve a rigid body problem based on concurrent force system as well as non-concurrent force system for 2D and as well as for 3D. Now I give you about 30 seconds break. So if any of you are having any questions or clarifications, you can ask. Anybody?
Sir, yeah, please, sir. Anything, sir?
Any doubt, Professor, from anyone?
Yeah, please, sir. Two people have raised their hands, and
Okay.
let me to come inside and ask the question, doubts to you, sir. Shivani and Joe Pascal, you have been allowed to come on live. Please come and ask your doubts with the professor, and please ensure connectivity. We are waiting. Please come as soon as possible. And until then, any questions?
Okay. So far, I have not
Yes,
received.
sir. Yes, sir. You can go ahead, sir. We have allowed people to come and ask the questions, but no one has come inside.
Okay,
Uh,
Professor.
yes, sir. Please, sir. Please, sir.
It is not coming again.
Yes, sir. Sir, minimize it. Yes, sir. Good, sir. Good, sir.
Now you are able to see, no, sir?
So we are able to see, sir. Yes, sir.
Yeah,
You can go
okay.
ahead.
Yeah, the students, if you are having any doubt at the end of the session, also you can ask me. Okay, don't worry.
Okay, okay,
Now
sir.
we
Yes,
move
sir.
to friction. So
Please,
another
sir.
important point about engineering mechanics is the learning friction. In day-to life, we are actually coming across so many applications for friction. One example is shown here. For example, Amazon or and many places are being mechanical engineering. You would have visited several companies, also industries there. The product will be moving from one place to another with the help of the belt conveyor. So the friction is very important between them. And when we are transferring power from one place to another with the help of the belt, for example, even in our household applications, like we have the grinder and motors, in so many places we use this belt friction. And sometimes even in the marine applications we see that we are actually using this. Of course, not only marine application, even as we farmers, we are using, to tie the cattle to the post. That time, how many turns we have to make? If you ask your grandfather, they will be able to tell us. Okay, they already knew friction, but not based on the equation, but by experience. So we are going to quickly see what is a friction, and one problem we are going to solve based on that. So when an object is kept on a surface, we know that the weight is going to act in the downward direction, which is W, and then there will be a reaction from the support, which is N. So we can remove this surface, and we can just replace that with the help of the reaction. So we can draw the free body diagram. But now if we apply certain horizontal force, then what will happen? This block will try to move towards right, but not immediately it will be moving. For example, when you apply the force gradually, you apply the force from 0 to say 1 kilonewton, but initially it will not be moving, but after certain time it will be moving towards right. But why it happens? When for instance, when I apply 0 newton, it is not moving. When I apply say 10 newton, it is not moving. 50 newton, it starts moving. Okay, that means before it starts moving, when we apply the force from 0 to 50 newton, there must be a reaction force coming from the surface which is equal in magnitude but opposite in sense. That's why this is not moving. Then only we will satisfy the equilibrium equation. So that reaction force coming from the two surfaces in contact is called the friction force. So this friction force will also be varying depending upon the externally applied force. For example, this W, there is a weight, and the N normal force, they are not going to vary because the weight is not going to vary and the normal force is not going to vary. But the applied force P is going to vary from 0 to 50 Newton. Let us say 0 to 50 Newton. So when the applied force is 0, the reaction force is, there is the friction force is also 0. When P is 10, the friction force is also 10 Newton. When it is 50, the friction force is also 50. But when the applied force P is 55, but still the friction force is 50 only. That means it has reached its saturation value, and thereafter, once it reaches its saturation value, whatever be the increment in the externally applied force, that is not going to increase the friction force. That means we say that that is the maximum friction force. So this is the fundamentals of friction, and then the friction force F is equal to, as long as the motion is not happening, as long as this is not moving, the friction force is equal to the applied force, F equal to P. But at the time of motion, that is when the motion is impending, we see that F has reached the maximum value, so it is called as Fm, which is equal to mu times N. So where mu is the coefficient of friction and N is the normal force. This coefficient of friction is actually depending upon the nature of materials in contact. For example, metal on metal means the range is 0.15 to 0.6 and so on. So once it starts moving, the slab or the box starts moving towards the right. That time you see there is a slight drop in the coefficient of friction. As long as the motion is not happening, the coefficient of friction is mu s. Once the motion is happening, the coefficient of friction is mu k. But from the practical experiments, it has been observed that the coefficient of kinematic coefficient of friction, no, that is actually slightly less than the static coefficient of friction. So that is what shown here. So till F reaches the F max, F is equal to P, linearly varying. It is equal. But once it reaches the maximum value, there is a small drop, and that is because of the reduction in the coefficient of friction. Now we see the same diagram is given, but you can see W is the externally, that means the weight of the object. Of course, that is also externally applied force. That's why we are showing it, because gravitational attraction, external force. So it is going to be same. That means it is not going to change. So the normal force is going to be equal to W. But now, in addition to the weight, we are applying certain force P, which is also acting in the downward direction. So now the normal force is equal to sum of these two, P plus W. But in the previous case, you would have seen that it is simply equal to W only, because P was not contributing anything vertical, it was only horizontal, that's why. So here the normal force is P plus W, and there is no friction force at all. Why? There is no horizontal force here. In the next case, instead of applying the force P vertical, we are going to apply with certain inclination. So this P is resolved into two components. One is Px and then Py, horizontal and vertical component. So the vertical component Py is to be added with W, so that will be equal to N. So N is equal to Py plus W, because this N is equal to vertical force W and then the vertical component Py. Whereas the horizontal force Px, applied force Px, is going to introduce a friction force F. So F is equal to Px, because F has not reached F max. That means the motion is not happening. So Px is equal to F. That's why it is said Px is less than Fm. Okay. In other words, I said no, 0 to 50 means it will be equal to the friction force, because F max is 50 Newton. So this Px is less than 50 Newton. For your understanding only, I am using the numerical number. So when the Px is less than Fm, okay, that is 50 Newton. That's why the motion is not happening. Now the externally applied force horizontal component Px, you see that Py and Px again, but we are increasing the Px. When we increase the Px, what will happen? It is going to match at one point of time with the maximum friction force. In other words, now Px has reached 50 Newton, which was taken as Fm. So that time the motion is impending. Okay, so again the normal force will be same force, N equal to Py plus W. Okay, so you can see the relation already we have seen. N is equal to Py plus W, because vertical component plus W. Fm is the maximum friction force, that is mu S times N, and then Fm equal to Px. Motion is impending, and still we are increasing the Px. So what will happen? Now Px is say 60 Newton. We know that the maximum friction force is 50. Beyond that it cannot go. So Px is greater than Fk, because now we, instead of Fm we call Fk, because It is a friction force associated with the movement which is slightly less than the static friction, and you see the motion is impending. So 4 cases, this is a very good example of what will happen when we change the externally applied force which will be trying to move the object. So no friction here, no motion, motion is impending, here it is moving. So this angle of static friction is very important. What is called angle of static friction? Because we know mu s is the coefficient of static friction, but there is another important term called angle of static friction, that is what shown here. This diagram is what we have seen previously, same diagram only, but what we have done here is, you see that W is very much there, this inclined force P is there, so we resolve it to Py Px, but instead of resolving, we are keeping it as a force only, P. So W is acting in the downward direction, P is acting like this. So here we know that there will be a normal force acting vertical direction, and the friction force will be acting here. So the resultant of friction and normal force is taken, that is the resultant force is taken. So the resultant force means the resultant obtained from the normal and F, SC here. So this is the friction force, this is the normal force. If you find the resultant of this, it will be acting in this quadrant, in the fourth quadrant. It is pointed upwards, and this angle is called phi. Okay, so if there is no horizontal force, what would have happened? It is like this, only vertical force. So the reaction is also like this. Here the angle of friction is 0, because here the friction force is 0, no? So what will happen? Phi also will be 0. So if you introduce Px, that will be introducing the friction force, so slowly the phi angle will increase. Again I increase Px from 10 to 20 Newton, F also will increase to 20 Newton, and I take the Px to 50 Newton, and the friction force also will be reaching 50 Newton. And at that point, beyond which F cannot go, that point what angle we have no, that angle is called phi s, that is the angle of static friction. Below that it will have some friction angle, but that is not associated with the impending motion. So here we take the motion is impending, that time the angle is called angle of static friction. So that is what you see, and from here using the tan theta you can find out tan phi s equal to F by m, and then F friction force is mu times n gets cancelled, finally we get tan phi s equal to mu s. So this is a very important relation. So phi s is the angle of static friction, that is the resultant of normal and friction force making with a vertical line, and then mu is the coefficient of static friction. This is a very important relation, and it holds good when the motion is impending also for the kinetic coefficient of friction. Now the angle of repose is another important point. Here from our childhood days we have been knowing what is the angle of repose. For example, when we were a child, definitely all of us would have attempted keeping a notebook or some flat surface. On top of that we keep some object, boxes or something, and from the horizontal position slowly we will be increasing the angle. At a particular angle we see that this box starts sliding towards us, that means towards the inclined direction to the bottom of the surface. So that angle is called angle of repose in simple words. So initially the surface, like here, initially we keep it horizontal, so that time the friction angle is 0 because no horizontal force is acting. But as we increase the angle of the inclination, what will happen? Still the weight will be acting in the vertical direction. It should be resolved into two components. One is perpendicular to the surface and other is along the surface. Okay, so the perpendicular is going to increase the normal force, and along the surface is going to try to move this one, that will be introducing a friction force in the opposite direction. So the friction force is acting in the opposite direction, and then from that we can find out what is the friction angle. Okay, so when the angle of inclination reaches with the angle of static friction, it will start sliding, and so this is called angle of repose. And this is for example, when the truck is unloading the sand, you see that it will make a cone. The sand or any powder type of material will be forming a cone. So that cone angle, okay, half of that, no, there is the angle of repose. So this is very much useful for various applications, right? So one example we see, and with that we move to the next one. Here you see there is a block B which needs to be moved up. So we use a wedge kind of thing. So here you see the block A is a kind of wedge, okay. So B is to be lifted with the help of wedge. For that we have to apply a force P from left. It is going to act towards left. That means block A will be moving towards left, so that B will be moving up. The weight of the block is given as 400 pounds. Okay, you know how to convert pounds into, because Dean Johnson, no, he has used the US unit system, but you can always convert into Newton, no problem. Here it is going to move up. So how much force we have to apply so that it can move up? That is the idea. So for that what we do, and two things are there. One is how much force we have to apply to raise the block, and then to lower the block. First let us take how much force we have to apply to raise the block. So this block B free body diagram we have to draw, and then wedge A free body diagram we have to draw. So block B is going to move up. So what are the reaction forces? When we draw the free body diagram of block B, we know that on the left side it is touching the surface, on the right side it is not touching the surface, so there will not be any reaction from this right side wall on B. But from the left side there will be a normal force coming from the wall, and since it is moving upward, the friction force will be acting, which is acting in the downward direction. So here you see, that is what you see here. This is the block B which needs to be lifted up. Here you see the reaction from the wall that is given. This is NB is the reaction from the wall, and the friction force is acting in the downward direction. Why? Because the block is moving up, that's why. And the weight 400 pounds is acting in the downward direction. It is very much there. The right side there is no reaction because you see that it is not touching the wall, but B and A are in contact. So what are the reaction forces from A on B? Because we are interested in drawing the free body diagram of B. So A is going to be removed, but in place of A, the reaction should be applied on B. So you see perpendicular to B, B is going to apply certain force on A in perpendicular to this surface. A is going to retaliate with the same magnitude in opposite direction. So we see that B, the reaction from wedge A, NA, is coming and acting in this direction. But only thing is the direction of the friction force is important. Here it is pretty straightforward, because here with respect to the left side it is moving up, so we are drawing the friction force in the downward direction. But sometimes it is confusing here whether we have to put the friction force towards left or towards right. So always we have to take the body of our interest, and then it should be compared with the body in contact. For example, here the wedge is in contact. So with respect to wedge, if you take a common point between B and A here, with respect to that point on A, B is moving towards right. Okay, so you take a point over here. Imagine that A is fixed. Now what will happen to B? B would have been moved towards right. So the friction force should be towards left. That is what you have here. So now we have drawn the free body diagram of block A. This is the weight, normal force from the wall, friction from the wall, normal force from wedge A, the friction from A. And here the coefficient of friction are given. From this we will be able to find out the unknowns. Sometimes it may not be possible. That time we have to draw the free body diagram of wedge A also. While drawing the wedge A, what are the forces here? You see the wedge is having a force P from here, and there will be a normal force from here, and since wedge is moving towards the left, the friction force will be towards the right. So that's what we have here, force P, reaction from the ground, and this is the friction force. But here you don't worry, whatever you have drawn here, no, these are the reaction forces from A on B. Reverse of that same magnitude should be applied. Here NA is acting upward, so here it should be downward NA. And then Here it is towards, the friction force is towards left, so here it should be towards right. And then using these two free body diagrams, we have to write the equilibrium equation, sigma fx 0, sigma fy 0, and then from that we'll be able to find out the unknown values. So that is the idea. Okay, so otherwise we can use an alternative approach, but you can explore on your own. It is also pretty straightforward. Okay, then there are several wedge related problems from the friction. So same concept you have to apply. So we move on to the next very important friction related application, that is the screw jack. And here you see, when we are applying a certain force on the lever, what will happen? The weight is going to be lifted or lowered. So this is a schematic representation of a mechanical screw jack. So here we have the base, and this is the screw, and then this is the cap on which weight will be applied. For example, it will be placed under the car or automobile, and then we are going to apply the force P at the end of the lever. So as it is rotating in the counterclockwise direction, here it will rotate because the direction of force is applied like this, so that it will be moving up. Okay, so how to solve this problem? Because after you become a design engineer, for a design engineer, the very fundamental subjects will be engineering mechanics and the mechanics of materials and design of machine elements. So in that, the very fundamental subject is engineering mechanics. Here you see, when we apply the, you should know what should be the weight it should be lifting up. So you have to ask the customer, and accordingly you are going to design this. To design the screw jack, you should know what is the force acting on that, what should be the friction, what is the helix angle of the screw. All those things are very important. So here, for example, not only there, you know that in the lathe and in several places you see that the garage will be moving on a square threaded screws. So there also you should know how to find out how to design the screw, lead screw, and further you should know how the forces will be acting on the screw. Okay, so I think all of you know what is a single start thread, double start thread, triple start thread, and what is the difference between pitch and lead. Pitch means you take any point on the thread and take the corresponding point in the immediate next thread. The distance between them is called a pitch. Lead is for one complete revolution of the screw, what is the axial movement of the screw, that is called lead. So for single start they will be same. For double start, the lead will be twice that of the pitch. For triple start, the lead will be 3 times of the pitch. So the other terminologies are there, but here due to short of time we are moving on. So this is the screw jack. Okay, how we are going to simplify this problem, like shown on the left side, so that we'll be able to find out how much force we have to apply or how much weight it can lift up. So this way already seen. So when we apply certain force P at the end of the lever, it is going to produce a moment on the screw. So what is the moment? It will be P times A. That is what we have here, PA. Okay, so PA is the moment created, and at the beginning of the slide we have seen there are equivalent couples. Okay, so that equivalent couple is equal to Q times R, where R is the radius of the screw, Q is the force that will be available at this point, because they are going to produce equal couple. Because when you apply here, you are going to produce a couple PA, and if you want to see if you move at a distance R, what will be the force available, that is Q. So this screw jack is going to be schematically represented as a block weighing the same weight W is being moved along the inclined surface. Okay, so this W is the same W what we have here. Okay, and then this force Q what we have calculated, this Q is not the force you apply at the lever. That you have to remember carefully, that Q is the force available at the end of the screw here at the pitch circle diameter. So that is the force Q, and this angle theta is the helix angle that you can find out from the lead, and then this 2 pi r. The height of the uh, triangular platform where we are moving, the height is L. This is nothing but the lead, what we have seen in the previous slide, and this length of the platform is actually 2 pi r, where r is the radius of the lead screw. So this W is the weight and the Q is the force available at the end of at the pitch circle point. Now if you find out how much force is required here, Q, then we will be able to find out how much force will be required at P. So here this theta is the inclination angle, here it is going to be the helix angle, and phi s is the angle of static friction. You know that the resultant of friction and the normal force will be making an angle of phi s when the motion is impending. So we have like this. So the impending motion upward, from this we will be able to find out how much force we have to apply Q. This is very similar to what we have seen before, but when we are trying to move in the opposite direction, because when we are trying to lift up, we have to apply more force, but it will not come automatically downward. We have to apply the force in the opposite direction at the end of the lever, so that the weight will be lowered down. So for that, what we do here, the same weight is acting, the normal force will be still perpendicular to the surface, but since it is going to be moved downwards, the friction force will be acting in the upward direction. There is a difference between when we try to lift up and lower down. When we are trying to lift up, because Q is applied, the block is going to move up in this direction. Okay, that time the friction force will be acting in the downward direction, whereas here we are going to move the block downward direction, so the friction force will be acting in the upward direction. That's why the resultant force changes its orientation. See here, the resultant force is acting in this direction, but earlier when the block was moving up, this is the resultant force. But here, two important point: while you are designing the screw jack, you have to be very careful whether it has the self-locking condition or not. Okay, so when the self-locking condition will happen is when the angle of static friction is more than that of the helix angle theta. So see here, it is a self-locking because phi s is more than theta. If theta is more than the phi s, what will happen? It will not be self-locking, and once you lift the car or a truck with the help of the screw jack, and then the moment you stop applying the force, since there is no self-locking, it will automatically, the weight of the truck will be forcing the screw jack to rotate, the lever to rotate in the counterclockwise direction, and the person below will be gone. So we have to be very careful about the self-locking condition, and you see that how we can achieve that with the help of the just by changing the angle of static friction is more than that of the helix angle. We can achieve that. So several examples, not only the screw jack, not only the lead screw in the lathe or in other places, or even in the like worm gear, no, here vice also is based on the screw jack mechanism only. One example problem is given here: how much force you have to apply so that it is tighten, or you may have to find out, for example, for various applications, no, we have to apply some adhesives between these two blocks, and then we have to apply a particular force so that this will be pasted together. After some time we can remove it and it will be fastened together. You have to calculate how much force we have to apply. It should not be too much, that will lead to breakage of this one, or if it is less means the sufficient force will not be applied. There also you have to calculate carefully how much force we have to apply. For that we need to know the friction. I leave this problem to solve on your own. It is available, as I said, that in Beer and Johnson book. So how to solve that problem is explained here. And another important point is the belt friction. Here this also is based on that concept. Here you see, this is a pulley or the drum on which the belt is located. It is wrapped on that, and on one side the tension will be more, and other side tension will be less. Here T2 is taken a high tension part, here it is a low tension part. So we should not think that both T1 and T2 are having the same force. If it is having the same force, definitely it will not be rotating at all, because equilibrium is achieved, no, equilibrium can be achieved in two aspects. One is like when the body is at rest or moving with constant speed, that time also we will achieve the equilibrium, we know that. But one thing is that here the power will be transferred only when they have two different tensions, and T2 is greater than T1. Here a small infinitesimal piece of belt is taken, and then the free body diagram is drawn, and then using the equilibrium equations, finally we can get this relation T2 over T1 equal to e power mu theta, where T2 is the high tension and T1 is the low tension. E to the power mu is beta, no, mu is the coefficient of static friction, that is the friction between the belt and the drum, and beta is the angle of contact. Here this is a very important point. This angle of the angle beta, no, which is going to be from here to here, P1 O P2 is the angle of contact beta, which should be put in radians and substitute here. From this we will be able to find out this T2. Sometimes we have to find out what is the coefficient of friction. Imagine that you are giving a drop of liquid, some lubricant between these two. Immediately you are greatly reducing the coefficient of friction, and you see that the power is not transmitted in any belt. Okay, so that is important, and the angle of contact is important. As the angle of contact goes more, we will be able to transfer more power. So this is an important equation, and an example is given here. There is a big drum, and then this is going to be driven by a motor which has a smaller pulley with that. As the motor rotates, this pulley is going to rotate, and so belt is going to move, and this will make this bigger thing to rotate. Now, as indicated here, determine the largest torque which can be exerted by the belt on pulley. So here we need to find out what is the maximum torque that is going to act on this one. And here there are two angle of contact. In the smaller pulley also has an angle of contact with the belt, and the bigger pulley is also having the angle of contact. So we may be tempted to choose this bigger pulley's angle of contact because it is huge, but we have to understand the lower smaller pulley is having a lower angle of contact, so that only should be taken for the maximum this thing. Please hold on the line. The battery is low. I will
Sir, you can go ahead, sir.
one
Please.
second, hold on.
No problem. No problem.
Yeah, sorry for that. We can continue here. So we have to take this as the angle of friction, and then we have to proceed. That is what shown here. So again we use the same expression, and we will be able to find out. Sometimes the power transmitted will not be sufficient, so two options before is we can increase the coefficient of friction by appropriately choosing the belt type, or we can increase the size of this smaller pulley to a bigger pulley, so that we can increase the theta value. That way also we can increase the power transfer. So this is the example. Another application is also shown here. You can find out. Similar concept should be applied. So, and then the last one is the rolling resistance. So in the sliding friction we have seen like various things like wedge friction, and then the screw friction, and then the belt friction. And then in the rolling resistance, actually unlike the sliding friction, the rolling friction study has not reached great heights. People have attempted, but still the not enough work has been done on the rolling resistance as compared with the sliding friction. Leave these two figures. Let us take the right extreme diagram, which will be sufficient to explain what is a rolling resistance. You know that weight will be acting, the weight of the drum, or if it is attached with the vehicle, then the weight coming to the wheel, no, that is W, and the force that is applied, driving force. Finally, you can treat it as a force acting at O. So P is acting here and weight is acting here. You know that. Now you can refer to the first diagram. the normal force will be acting and the friction force will be acting. The resultant of NF is the resultant force, which is shown over here. Okay, so now these are the three forces. W is the weight which is going to act on the wheel, and P is the force which is trying to move this forward, and R is the reaction force here. And then if we take the moment, only three forces are acting, and if three forces are acting and then the body is in equilibrium means then all the three forces must be passing through the single point. But there are some exceptions. For example, if you take the horizontal beam, its self weight will be acting at its center, but the reactions will be acting at extremes. But only three forces are acting; they are in equilibrium, but still they are not passing through the single point. So we have to say if three forces are acting at one of the forces making certain, if they are not parallel, then we can say that they will be passing through the single point. Now, if we take the moment about point B, then R will not produce any moment, but P times R will be moment acting in one direction, and W times B. This B is the distance between O, horizontal distance O and B. So there is a small b. So we take the moment P R equal to WB. So from this we can find out the B, this B value, which is called the coefficient of rolling resistance. Unlike the coefficient of static friction, which is a dimensionless quantity, here it is actually in terms of mm or inches. Okay, so rolling resistance is very important because if the B value is more, as you know, that's why we call that if we have to inflate the tire properly. If it is not inflated properly, what will happen? B value will be more. If B value is more means the coefficient of rolling resistance is more, that means we have to increase B value. If this value is very small, then what will happen? B value, then the resistance will be less. That's why we go for trains. No, it is a rigid body. If it is unlike a tire, it is a iron, then the B value will be very small, so we can reduce the rolling resistance. So this is very important from the transport point of view, which also we need to know. So with that we complete the friction. If there is any questions or clarifications, I can wait for 15 seconds and you can raise it.
Sir, let me look into the chat box for any questions.
You can ask them to unmute their mic and then ask, sir, so that I will be able to.
Actually, I am allowing them to come inside, sir, but they are because of the connectivity, they are not coming inside.
Okay, no problem, sir, because they may want also to wait till I complete it. Then we can start. No.
I am allowing. Dear participants, I am allowing who are raising your hands. So if you have proper connectivity, please get in and you can clarify your doubt with Professor. Let us take one or two questions, sir, if it is in chat box.
Since I am not able to see the chat box,
I read the question, sir.
Okay, sir.
No problem. Yeah.
Okay, so probably you want to ask at the end of the session. How much time is left, sir, for me now?
Sir, you can go with your comfortable timing, sir. No problem, sir.
Actually, the scheduled time is 9:30 to 11, isn't it, sir?
11. Yes, sir. Yes, sir. Yes,
okay, sir. Because I should not take too much of a participant's time. Okay, so now we can take the truss. Probably this will be the last part, I think. So truss is another important application involving mechanics, and you see that here hangers and like these trusses, and then bridges made of truss, and space applications like that lab space lab. No, they are also having various truss applications. So what is a truss? Truss is a stationary and a two-force member. That means the force will be acting along the axis of the rod. It is a two-force member means these two forces will be acting along the same line and it will be having the opposite direction so that it will be in equilibrium. So other definitions I am not going to explain. And here there are rigid truss which we want to use. For example, here we have ABC as a rigid truss, and it has when you apply the load here at point B, it will not collapse. But imagine a quadrilateral truss, when we apply the load at point B, it will be collapsing. So we have to be very careful about the type of truss. Here you see the simple truss. Simple truss means they are made up of a triangular form. So you can see everywhere it is of that nature. And then there are various names given. Each one has its own advantages, and you see that. And this is the actual photography taken for a truss. But for simplification problem, we just first convert like this at point A, C, D, not exactly this one, but you can see that they are having several rivet or bolts, and then we convert into like this, so that we can analyze it easily. Several simplifications are made while solving the problem, as you see. And then here you see there are two methods to solve the truss problem. One is the method of joints, the other is method of sections. So both are having some advantages, and we are going to see both the methods. In method of joints, you see we start from each joint, and then we progressively move to the interesting or the joint in which we are interested. For example, here we take A, D, B, C. It is a truss, and then at point B, it must have been a roller support. That's why only the reaction is RB. Whereas this should be a hinge type. That's why we have a horizontal vertical forces. The resultant is RA, or you can take it as a horizontal vertical components also. Now, if you want to draw the free body diagram of the joint and then individual members, it will be looking like this. For example, let us take point B. Already it is having RB. That's why you see that this is a point B and it has RB. And then point B is attached with the point C and D through the members CB and DB. So the force will be acting along CB and DB. That's why you see that this is the force DB and this is force CB. Okay, but one thing is the direction could be reverse also. We do not know at the beginning, but only thing is the line of action is known, and then we can modify it. And if you take BC rod, this is the BC rod, and it is a truss, so it will be having the axial force only. And you know that if you take the point B, this force is applied by this rod on point B. So same magnitude but opposite sense is this force which is applied by point B on the rod. So we have to be very careful. That means in what direction here also, if you are applying the same direction, then while solving you may make mistake. So if you take the point C, there is a joint C, then you see what are the forces acting on that. CD is applying a certain force on C, that is what here, and the BC is acting here, and then AC here. Like that, we have to draw the free body diagram of the joints. We are interested in the joints. Now, how to solve a truss problem by method of joints? So this is the given truss, and this truss is having a roller support at point E and then a hinge support at C. First, we have to take the whole truss as a single body and then remove the roller support and as well as the hinge support and replace them with the forces. So if you remove the hinge, there will be two forces. Two forces means the two components of a reaction force. So horizontal, vertical. Here only a vertical force. That is what we do here. So this diagram is the free body diagram of the total truss. This roller support is removed and then reaction force is introduced. The hinge support is removed and the reaction components, horizontal, vertical components CX, CY are introduced. Now we are going to use the method of joints to solve this. Okay, so how to do that? Let us take a joint. Any joint we can take, but provided it satisfies our condition. So once we have the total free body, we will be able to find out CY, CX, E, because this total free body diagram, we know what is this value, 2000 pounds, 1000 pounds, but we do not know the reaction from the roller support. Also, we do not know the reaction from the hinge support. So three unknowns are here: CX, CY, or E. And this is a two-dimensional rigid body. For two-dimensional rigid body, we have three equations, equilibrium equations, sigma fx0, sigma fy0, and sigma mz0. So three equations and three unknowns. So we will be able to find out Cx, Cy, and Re. But we are interested in the force acting, say at point D or at point B. So in that case, what we do, again we take this whole system and let us start from any joint which will have least number of forces. For example, you are free to choose point A. You can start from A and then you can come to D or come to B. Otherwise, you can start from C and then come to E and then you can come to D also. Why? But you cannot directly start point B. Why? If we start A, then three forces are acting at point A as indicated here. This is the point A. This 2000 pounds is acting here in the downward direction, and FAD and FAB are going to act. So that is what shown here. So three forces are acting, and the point joint A is in equilibrium. Then we will be able to find out by using the Lamb's theorem, or that by resolving we can find out. Here, while solving the forces at joint A, it becomes a particle. So see the difference. Earlier, while solving this one, the whole truss was taken. It was taken as a 2D rigid body. That's why we were able to use three equations, sigma fx0, sigma fy0, sigma mz0. Now we are taking the joint A. Joint A is a particle. For a particle which has a 2D forces, then there will be only two equations, sigma fx0, sigma fy0. There is no moment involved in that because it's a particle. So we will be able to solve only two unknowns. So we have to ensure that there are only two unknowns. Of course, here FAB, FAD are the two unknowns. So we will be able to find out FAB, FAD. So once you know FAB, FAD, then you can take point D, then these two forces you can find out, then you can go to B. But had you taken B at the beginning, you know only 1000 lb, but you do not know FAB, you do not know FBD, you do not know FBE, FBC also not known. So we should not have started with B. Similarly, we should not have started with D because these three forces we do not know. We should not have started with E also because these three forces we would not know. Because everywhere the joints will be taken as a particle, and then only two unknowns can be solved using sigma fx, sigma fy0. That's why you start from A or you start from C, because when you take C, these are the two unknown forces. We will be able to find out these two unknowns using those two equilibrium equations. So that way we can progress. This is called the method of joints. Right. So method of sections is actually a simpler method than the method of joint from one aspect, that we don't have to progressively move from A to that point. This is a simple truss. At the beginning of the slide, we have seen a truss which is having so many joints. So we cannot start from one end. Slowly we can't move there. So there and all we use the method of sections as a convenient option. So here you can take any imaginary cutting plane and cut as you wish at any section, and then take the one part of the rigid body or the other part of the rigid body, and then you can try to solve. And the section need not be a straight line, it could be a curve also. Like this also you can cut as you wish, you can cut, no problem. And here you cut like this, and then you are taking the left side part ABC, and then here instead of showing this cut part of the member, what you do, you can even remove them, because the forces are sliding vectors for rigid bodies. So doesn't matter whether you have here this part, no, the small part can be removed and directly you can take the forces acting. That is how these small broken pieces are removed and then directly the forces are shown. So you take like this. Now this is a rigid body. Since it is a two-dimensional rigid body, three equations will be there: sigma fx, sigma fy, sigma mz0. From that you will be able to find out three unknowns. We can find. Otherwise you could have taken the right side part of the remaining body and then you will be able to solve. And for both the problems, method of joints and method of sections, at the beginning we have to take the total truss as a single rigid body, and then we have to find out the reaction forces coming from the support, and then we adopt the method of sections or the method of joints. For example, here under method of sections, this problem is solved. Here you see, and then a truss is given. Now we want to find out FEF and FGA, the force acting between GA. What is the force acting on the member? We have to find out, and EF. So this force we have to find one vertical component, one horizontal component. So for that, how to solve? As we discussed it before, first you take the whole body, remove these two supports and introduce the reaction forces, and then take the whole rigid body, and then you can solve for the unknowns. So they are actually reactions like um, here and here. So we know Bx, By, J, three unknown. Thereafter, what we do? We use the cutting sections, imaginary cut planes, MM, NN, like that. So if you want to find out the reaction force along EF, means you have to ensure the cut section is passing through that point. If you want to find out the force acting along EF, then N imaginary cutting plane is to be chosen, and then it will be cutting here. That is what shown here. After cutting, E is here, and as I said, the broken pieces you don't have to show because the force alone is shown. So EG and EF, they are shown here. EG and EF. Similarly here, DF is shown here. Now there are three unknowns. Why? Because already we have calculated the reaction by taking it as a whole body. No. Now only three forces F, EG, FEF, FDF. These are the three unknowns. Again, this is a rigid body 2D. So three equations, we can solve those unknowns. Similarly, the right side also we can find out. So this way we can find out the unknown forces acting at any member without starting from any one of the ends. And then the classification of truss is important because we are interested in taking the statically determinate truss, not statically indeterminate. You know what is determinate? Because if the number of equations available and the number of unknowns to be found out are equal, then we call it as a statically determinate problem. If the number of unknowns are more than the number of equations, then we call it as a statically indeterminate problem. So in the truss, there is an equation for that. Here m is the number of members, n is the number of joints, and the relation between them is like this. Then it will be a statically determinate problem. This is rephrased like 2n equal to m plus 3, where m is the number of members, n is the number of joints. So as long as this 2n is equal to m plus 3, this is a statically determinate problem. For example, we can check whether this is statically determinate problem. How many joints are here? 1, 2, 3, 4. 4 joints. So 4 into 2, 8 on the left side. On the right side, m plus 3, number of members 1, 2, 3, 4, 5. So 5 plus 3, 8. So this is a statically determinate problem. Whereas here, you see 4 joints, so like here only, but one member is introduced extra. There is a difference between these two. So again on the left side we have joints, 8 joints, but here instead of 5 we have 6 members, so it will be 9. So this becomes a statically indeterminate problem. So 2n is less than m plus 3, so this is a statically indeterminate truss. But what will happen if 2n is greater than m plus 3? This is a non-rigid truss. That means it is no longer a truss. At least any one of these two only we have to use. And this is whatever we have seen so far is a 2D truss, but sometimes we may have to take a 3D truss, which is called a space truss, and for them the same equation. Here you see m equal to 2n minus 3. No, this is for 2D truss. For 3D truss it will be m equal to 3n minus 6. Now a question may come to our mind, why these 2, 3 are here, and here it is 3 and 6, and here the minus 3 minus this value indicate the rigid body modes. There is a translation along x, translation along y, and rotation about z. In case of 3D, it will be translation along x, y, z, rotation about x, y, z. That's why the rigid body modes are to be subtracted. This is a 3D problem, so joint will have that 3 movements. So this is actually 3. In case of 2D, it is 2. That's why. So otherwise, no, it is very similar to the 2D truss. In case of 2D, we take a triangle to construct the truss. In case of space truss, it will be a tetrahedron. You can see. And then next is another tetrahedron will be added, and we can proceed making the space truss. If you visit many places like airport and hangars in or space labs and various places, we use the trusses, space trusses to get the structure, which is actually very less material we are going to use, and then construction is easy, and then we can make very big constructions. There is the advantage of space truss. With that, we complete the truss. Next is the I think how much time left? It is 11:04. So probably 10 minutes I will take because I started at 9:38. So I can go till 11:10. But
Please, sir, please.
yes, sir. When is the next session, sir?
Sir, next session only 2 o'clock only, sir. No, 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 no.
Okay, then 10 minutes probably I can
Yeah.
take so that I can wind up covering the statics of mechanics.
Fine, sir.
So next important point is center of gravity, but you don't need that much introduction about the center of gravity because from your school days probably you would have learned. But what I want you to focus is this final equation. This W is equal to integral of dW. That is the total weight of the body, rigid body, can be found out by summing up the infinitesimal weight of the body. Okay, so for example, here you take an infinitesimally small element whose weight is delta W. Similarly, if we add all the weight, then we will get the total weight W. And then we see that this derivation you would have done already, so I don't want to take time. So x bar W is equal to integral of x dW. So this dW, we know the infinitesimal element weight, and x is the location of that infinitesimally small weight from the origin. So x dW is the first moment of that weight. That way also we can define, because dW, it is like a moment of your force. No, what is a moment of your force? It is r cross f. Otherwise, the distance times the force. Similarly, here it is the first moment of the weight. So the weight is Tw for the small element. It is located at distance x. So it is located at distance x, and so this is with respect to y-axis. With respect to y-axis, what is the location of that? X times delta W. If we find out the product and integrate over the entire area, entire volume, then we will get x bar W. From this, we can find out x bar. X bar is the centroid of that rigid body. Similarly, we can find out y bar also. This is the other centroid coordinate. And then if we remove the from the weight, you can remove the like acceleration due to gravity, and then we can remove from the, then we will get the density, then remove the, then we can convert to mass, and then volume. From the volume we remove the thickness, finally we get the area. So the same equation, but it could be write as W is integral of dW, no, so it, and x bar W is equal to integral of x dW. This can be written as x bar volume V is equal to integral of x dV. Otherwise, it could be x bar m is equal to integral of x dm, and then we can write x bar a is equal to integral of x dA. That is what is done over here, but this is very important. X bar a is equal to integral of x dA. No? So we can find out, to find out the centroid of the area. This is a very, very important property. So x bar a is equal to integral of x dA, x bar equal to integral of x dA by a, y bar is equal to integral of y dA by a. So these are called, this is called first moment of area with respect to y-axis. This is first moment of area with respect to x-axis, because with respect to x-axis we measure the y coordinate here. That's why. And then the centroid is the same thing is repeated here, and then centroid, because this centroid of area, similarly we can have the centroid of lines. This is also important. For example, we have a wire, a rope, and then a chains. That time we will have to find out the centroids. That is what shown over here. So here, as we have seen before, here it is like x bar a equal to integral of x dA. Here x bar l equal to integral of x dl. That means we take the infinitesimally small length dl, and what is its location from the y-axis x, and then so this is the first moment of that length, and then for the total length we have to integrate and add, that will be x bar l. L is the total length of the line, and then from that we can get x bar. Similarly, y bar, which are centroids of the lines. So again we come back to first moment of area. In the first moment of area you see qy is equal to integral of x dA. So this is the first moment of area with respect to y axis. This is integral of x dA. First moment of area with respect to x axis, integral of y dA, which is given like this. So if an object, for example here, let us focus on this diagram, which is symmetric about y axis but not symmetric about x axis. But if it is symmetric about y axis, then we see the first moment of area about y axis will be 0. That means this will be 0. Why? Because it is symmetric. So what? Here, if you take two infinitesimal elements which are equally located on either side of the y axis, so this dA, which is located at distance x, the same infinitesimal area located on the other side with the minus x. So when we integrate, what will happen? X dA plus of minus x dA, so they will cancel out each other. So finally we have 0. So from this what we infer is, if an area is symmetric about an axis, then the first moment of area about that axis is 0. What is the use of this statement? The reverse is very useful for us. If the first moment of area is 0 about an axis, then that will be the symmetric axis. So that we will use that symmetric axis. Why we have to use the symmetric axis? Because if you know the symmetric axis, to the intersection of two symmetric axes will give us the centroid of that area, which is very important for us in calculation. So that is what we see here. So here the first moment of area about y axis is 0, but the first moment of area x axis is not 0. Here you see that this B dash is actually the symmetric axis for this area, and obviously we can understand that the first moment of area is 0. Otherwise, about this axis the first moment of area is 0, so we can say B dash is the symmetric axis for that. Some other examples are shown here. See, the B dash is the first moment of area about B dash and D dash are 0, so the intersection is going to give us the centroid. Similarly, here also we get the centroid. These are the important use of the first moment of area. In addition to that, in theory of machines and then in the kinematics, no, that time will be frequently coming across, especially in dealing with the theory of machines and or in the mechanics of materials. Whenever the first moment of area term will be appearing here and there, and then to deal with that also we need to know the first moment of area. And I see here it looks like immediately on first side we would be saying that it is not symmetric. This z is not symmetric about y axis or z axis, but still the first moment of area is 0. That is the interesting thing about it, because when we take the first moment of area about y axis, what will happen? For every area located above x-axis, there is another area located below x-axis at equidistance. Okay, so here dA, if you take, it is located distance plus y. Here on the other side is located minus dy, so it will be 0. So x-axis is a symmetric axis. Similarly, y with respect to y also it holds good. So intersection y is going to be the symmetric. Y is going to be the centroid because they are intersection of the symmetric axis. So the centroids are very important for the area and the lines. That's what we have here, and you can go through it. Some of them we have to recollect immediately. Some of them we don't have to. We can refer the book. And then the composite areas will be given. We will have to find out the centroid. To find out the centroid, we use the first moment of area. And here, why we have these things is like if you know some standard shapes to find out the centroid, then we can find out using them for the complex areas. For example, here we have a triangle and we have a circle, and how to find out the centroid of this is by adding the square and triangle and the semicircle. Finally, we can subtract the circle so that we get the whole here. So that way we can have, and you find out sigma a, and then the first moment of area about y-axis, the first moment of area about x-axis you find out, and then finally you get the centroid, because this divided by area will give you y bar, this divided by area will give you the x bar. So for that we need to know the first moment of area, and there are several other approaches also there. We don't have to worry about it. When time permits, you can go through it. And two important theorems are there for that means a geometric property, because whatever we discuss now, no, this is like area property. We are concerned about the area only. Okay, so here two theorems which are very helpful to find out the centroids or the surface areas, or to find out the volume are given. So the theorem of Pappus-Billness is a very important theorem. The theorem 1 says that the area of a surface of revolution is equal to the length of the generating curve times the distance traveled by the centroid while the surface is being generated. This simple only, don't worry. For example, here you have a semicircular arc, and we are going to rotate this semicircular arc. It is going to be revolved about the axis AC. Then what we get is a sphere, hollow sphere we are going to get. Now we are interested in finding the surface area of the sphere. For that, what we have to do is we have to find out the product of the length of the curve. So we have to take the length of the curve. The length of the curve is like, here it is a semicircular arc, so it is going to be pi r, that is the length of the arc, times the distance traveled by the centroid of this arc. So we have to find out the centroid of this arc. It is going to be 2r by pi. From here it is going to be 2r, because here you can see the centroid, no, 2r by pi from the axis. The same thing is what we take here. The centroid C is from here 2r by pi. So we have to multiply the distance traveled by the centroid. How much distance it would have traveled when you make one complete rotation about this revolution about this axis. So it is going to be 2 pi r. R is nothing but this 2r by pi. Okay, so in that case it will be 4r. That is what we will get. See carefully, the distance traveled by the centroid. Okay, what is the distance when we revolve this around 360 degrees? We are going to revolve this semicircular arc about this axis around 360 degrees, means the point C also would have rotated around 360 degrees. So it would have made a circle, but that circle will be coming towards us. It will be perpendicular to us. So this will be there and coming towards us, and then finally it will complete one circle and it will go. So what is the length of that one? It is going to be 2 pi times this 2r by pi. So it will be 4r. That is the distance traveled by, times the length of the r. So it is going to be pi r. So pi r times 4r will give us 4 pi r squared. That is the surface area generated by this curve. That is what Pappus and Gallner says. Okay, so this is applicable for anything. For example, here you have an inclined line, and then when it completes one circle, then the surface area will be equal to the product of the length of the line and times the distance traveled by its centroid. Centroid you have to find out with respect to the axis about which we are rotating, and then so we will get the surface area of the cone. And here a circle is given, and it is going to be revolved about this. Is like a tube, cycle tube or a car tire tube we are going to get, and we can find out the surface area, the total surface area we can find out. And there is no need that it should be rotating complete 360 degree. It could be any angle also, no problem, but it should be in radians. It should be like a 60 degree or 124.5, doesn't matter. Still we will be able to find out the surface area. And this is very useful when you are actually using the modeling packages like ProE, CATIA or Inventor, all those things. Why? You have a surface and immediately you see that what is the surface area, that just by click you are getting, they calculate by using this thing only. This is it looks like a complex shape, but easily you can find out what is the surface area by using this concept only, because this is generated with the help of a arc as indicated here, and then you are going to rotate about this vertical axis so that you get this surface. So how to find out the surface? For that we have to simply multiply the length of this arc times the distance traveled by the centroid. So here the length is actually, it is 1/4 of a full circle, so it is going to be pi r by 2. That is what we have. This is the distance traveled by the centroid, so we get the surface area. The second theorem is very similar to what we have discussed before, but in the previous case we discussed about the surface area, but here it is going to be the volume of the body. So earlier we were rotating the line, but here we are going to rotate the like area. Here we take a semicircle, and the semicircle is going to be rotated about this axis. So when we are rotating about this axis, what we will get is again a sphere, but now we are going to get a solid sphere. Earlier we were getting a hollow sphere, but here it is a solid sphere. Now we want to find out the volume of the sphere. For that, we can use the Pappus and Gallner's theorem. Earlier, we were multiplying the length of the line times the distance traveled by the centroid. Here also, we are going to take the same thing, distance traveled by the centroid, but multiply by area. You can do it on your own and you can find out. This way you can find out the sphere, cylinder, like that, so that you can verify on your own. But for practical application, we are using it for very complex shapes, so that we'll be able to find out the volume of shapes. Only thing is that the line should not be intersecting each other. That is the important point. Okay, like this you can find out cone torus, but primarily it is useful for complex shapes. And then the center of gravity also you can find out as we have done before, and these are some examples how to the center of gravity for some standard shapes. And then for different shapes, how we can find out by adding or subtracting. Here you see that this is a cylinder, left side there is a hemisphere attached with it, but there is a cone type of volume is removed. So we can take it as a cone full cylinder, and then it should be subtracted by the cone, so that we will get the actual shape. Further, how to find out the center of gravity or the center of the volume, same approach should be used to find out. The last topic is the second moment of inertia. The second moment of area, this is called the moment of inertia. It is very similar to the first moment of area. There it was actually integral of x dA, means it is integral of x square dA, that's it. We have to take one more moment, that's why it is called the second moment. Here you focus only this equation. Ix is, sir? Hello?
Yes, sir. Yes, sir. Please go on, sir. Please go on, sir. Please go on.
Yes, sir. Yes, sir. This second topic, what is time? Oh, 21. Okay. Sorry, I did not notice. This I will stop, sir.
Sir, no problem, sir. If you are comfortable, please go on, sir.
Okay, sir. Because I just I can take no problem to us, but I'm concerned about the participants. Beyond 1 or 30 minutes, no, whatever we teach will not reach them. That's why. But this is an important topic, so I will wind up in 2 minutes, sir.
Yes, sir. Please, sir. Please, sir.
Yeah. So the second moment of area is important. So this Ix equal to integral of y square dA, because we take the second moment. Because the simple example is, if you take your scale, that measuring scale, what we use to draw lines, no, the lengthy scale, you can bend it easily when you keep it flat. But if you keep it vertical, then you find it difficult to bend. The reason is the resistance. When you keep vertical, the cross section area will have more second moment of area or moment of inertia. That's why we have to be very very much interested in learning the second moment of area. So that's why you see that even the rail, rail tracks are having the I section, or even the sometimes the pole post, no, they are having the cross section, high cross section, because you are throwing away more material from the axis of the bending, which is called a neutral axis. And the first moment of area and second moment of area are actually simply mathematical expression, but when they are combined with certain application, for example, in the strength of materials, beam is there, we have to use the flexure formula, no? There EI is the flexural rigidity, where E is the elasticity modulus multiplied with I is the moment of inertia. So there it is useful. Similarly, at many places it is useful. So that is the second moment of area. The difference between first moment of area and second moment of area is, the first moment of area can be positive, or it can be negative, or it can be zero also. But the second moment of area will always be positive. Okay, so there are several approaches for that. We can leave it. The last part is the radius of gyration for that. So what is the radius of gyration? Frequently we will be coming across the radius of gyration. See here, you can see there is an area given here. Now we want to find out the radius of gyration, means first we have to find out the second moment of area. For example, with respect to x-axis or y-axis, we can find out. So here, with respect to x-axis, we find out. With respect to x-axis, we find out the first moment, second moment of area, or simply moment of inertia. That value we keep. There is going to be kx squared ix value, and this surface is going to be made as a very thin strip. And then at what distance we have to place the thin strip so that we will be getting the same moment of inertia of this area. So that distance is called the radius of gyration. So similarly, with respect to x-axis, see, this is the area. It may be having a particular area, say 1 meter squared something, and then you make it as a very thin strip. The thickness is say 1 mm. This is only for your understanding I am saying, but literally it should not be having any thickness. So then you make it as a thin strip, and at what distance kx you have to place so that the thin strip, but it can be going anywhere like this, having the same moment of inertia of this one, that is called radius of gyration. So kx is equal to ix by a. Ix is the second moment of area you found out. Similarly, the strip can be placed like this or like this, then we can get, or the polar moment, from the polar moment of inertia, which is the sum of the moment of inertia about x and y axis also we have. So polar moment of inertia also can be used to find out the radius of gyration. But here the radius of gyration from the polar moment of inertia is obtained by assuming that the area is made as a thin hollow cylinder, so that it will be having the same moment, polar moment of inertia, this one. So with this I'm minding up, because I was supposed to be stopping at 11, 10 or 15. So my 10 minutes I took extra, because so that I can be doing some justice that I completed, or completed means touched upon, because this topic, whatever I have covered up to now, should be taking at least some 15 hours. Okay, so within this 1.5 hours, I covered to a larger extent. So that if it is benefiting for you, then I'll be happy. The purpose of arranging this talk is now the session is open for discussion. If you have any discussion needed, you can unmute your mic and then you can come out. Otherwise, professor can facilitate that. Thank you.
The question, excuse me, sir.
Yeah.
The question is asked by Joe Pascal.
Okay.
Sir, can you please explain the rocker support reaction?
Rocker support reaction.
Yes, sir.
Okay. Here, 1, 2. Are you able to see this? This one?
Yes,
Yes,
sir. Yes,
sir.
sir.
Fine. So here you see the rocker is very similar to the roller support. You see these two. Okay. So the roller is going to have a vertical reaction, because if you move this, what will happen? The roller is also going to move, but at any point there will be a point contact. There is a theoretical assumption, but practically also, if you see, there will be a small contact only here. So the reaction force will be in the point of contact in the normal direction to the surface. So it will be acting vertical. Similarly, here also, when you are trying to move this, what will happen? This may be slightly tilting also, no problem. At the point of contact, which has been shifted from the present point of contact to some other point, there also it will be perpendicular to the surface of contact. So again, it will be vertical only. So that's why the rocker and as well as the roller are having the same reaction force. That is simply perpendicular to the surface of contact. Yes. Convinced?
Sorry for disturbance. One participant, Kasi has come online.
Yes, sir.
Hello, sir.
Please, you can ask a doubt with the sir.
Hello, sir. Good morning,
please.
sir.
Yeah, good morning.
Sir, this is Kasirajan from Pollachi.
Okay, Kasi, எப்படி இருக்கீங்க? How are you?
நல்லா இருக்கு, sir. நல்லா இருக்கு, sir. Sir, can you
Nice
explain the... Okay,
nice
sir.
to hear from you. Please go ahead. Yeah.
Thank you, sir. Very good lecture, sir.
Oh, thank you. Kind of you. Yeah, please.
Sir, can you explain me the exact difference between moment of inertia and radius of gyration? How can be it can be explained in practical manner, sir.
Okay. So moment of inertia and radius of gyration, isn't it?
Yes, sir. Yes, sir. Yes, sir.
Okay. So here again probably the last slide I was discussing, no?
Yes, sir. Last slide was about radius of gyration, sir.
Yes, yes. Because probably because of the time constraint, I made a rush, but I'll be happy to spend some more time on that.
Okay.
It's here. This is the given area.
Okay, sir.
So this area is given. It could be of regular shape or irregular shape, and we know that the second moment of area, which is also called as moment of inertia, but sometimes we may be confused with the mass moment of inertia,
Yes, sir.
because the mass moment of inertia is actually there. I'll show you that. Okay, if here I kept it, but due to shortage of time, I was not. This is the mass moment of inertia. Okay,
Oh,
see, this is a rigid body, and then we have the rigid body, and then this rigid body, very similar to what we had before. Here, earlier, we were having I is equal to x squared dA for area. So, x dA means first moment of area, x squared dA means second moment of area. But
okay.
here, instead of x, we are having r squared, so no problem. But instead of dA, we have dm. That means we take an infinitesimally small element whose mass is dm, and then that should be multiplied with the distance from the axis of our interest. So it is going to be x dm. But the first moment of mass moment of inertia is not having any significance. That's why we are not using it. But
Okay.
the second moment of inertia, that is again the second, the again the first moment of area mass is multiplied by one more time, so it becomes a second moment of mass, that is the second mass moment of inertia. But since we do not use the first mass moment of inertia, we whenever we say mass moment of inertia, it refers to simply integral of x squared dm, or it is r squared dm. So
Okay.
that is the mass moment of inertia. But uh, if you say the second moment of area are sometimes simply called as moment of inertia. So people, to avoid ambiguity, we can call it as a mass moment of inertia or area moment of inertia, so that we can understand easily.
Okay.
Though it is referred by various things. So here also same thing. Like you take the infinitesimally small element, and then what's its location from the axis, take the distance, square it, and then the product of that is the second mass, the mass moment of inertia of that small element. Then if we integrate over the total mass, then we get the total mass moment of inertia. So that is the thing. But actually here, for the mass moment of inertia also we can have the radius of gyration. But here what we frequently use is the radius of gyration for areas. That is very much useful for us. Here we take this area, this is the given area, it could be of any shape.
Okay.
Now, if you want to find out the second moment of area, now mass is not at all coming into picture, only area is there. With respect to area only we are discussing. So, the second moment of area we want to find out for this area with respect to x-axis, means what we will do, again we will take an infinitesimally small area, and we will have I x is equal to integral of y square dA. Otherwise, with respect to y means it is going to be integral of x squared into dA.
Yes.
So, with respect to x-axis, we can find out using that approach, and that value we can take it as, for example, I y, like that, or ix, depending upon the this thing. Then what we do, this is what we want actually, but sometimes what we feel is this area is distributed like this. But if we have a term which will assume the total area is distributed at equal distance from the axis. See here, if you take this area, for example, let us take a small area which is far away from the x-axis. If you take another small area which is closer to x, it will have a different x value or y value here, isn't it? So what we do, we take this entire area and then we make it as a very very thin strip, so that when we place this thin strip, it is like each and every infinitesimally small element will be located at the same distance from the x-axis. So for a rough understanding, I say a layman understanding, so that, but why I say this is we should not take it as the exact thing, but for understanding purpose only, let us take. So this has an area of say 1 meter square. Now we want to, this total area is 1 meter square, and depending upon where we place this origin, the second moment of area will change. Okay, so what I do for this 1 meter square area, I'm going to make it as a thin strip such that its thickness is very very small, say 1 mm. In that case, what will happen, the length will be very very huge, it will be going on either side to a larger distance, but doesn't matter. If you are taking now a small element here or some other place, they are at equidistance from the x-axis. So instead of the area being distributed at a different distance from the axis of interest, if you assume they are to be located at same distance from the axis, and the distance at which they can be placed to produce the same moment of area, the second moment of area is called kx. So this value will remain the same always, we are not going to be changing this one, kx will remain the same. That is the idea. So this is for some uh, uh, frequently in theory of machines we will be coming out with this term, that's why we call it as a radius of gyration. Similarly here also, for the same area, if you want to find out the polar moment of inertia, then what we do, we are going to find out ixx, then iyy, then using the perpendicular axis theorem, the sum of these ixx and iyy will give us the polar moment of inertia about z axis. We know that value we calculate, that is going to be jo. Okay, otherwise it is jo, we can take jo. And what we do thereafter, this will be made as a very very thin hollow cylinder. That thin hollow cylinder is placed like this. Now, at what should be the radius of such a thin strip, so that we will be getting the same polar moment of inertia for this area. So that radial distance is called radius of gyration. So that we have J for this. What will be the what will be the polar moment of inertia? It is going to be a times k naught squared. If you are having a same thin hollow cylinder, it will be k naught squared a, that is r squared a, no? So k naught squared a, instead of r we call ko, because it's the radius of gyration, since we have given a specific name for that. So k naught squared a, what is this j naught? This is the j naught of this area which we calculated by summing up this one. So we have calculated this go from here, area is also for this area only, but k naught we found out, but that will give the physical meaning like this. Is this clear, Dr. Kasirajan, now?
Yes, sir. Yes, sir. Thank you, sir.
Okay, thank you.
So much for wonderful explanation.
Thank you.
Swapna, you can ask a question if.
Okay, sir. The question is asked by Abhinash Nayak, sir.
Okay.
How 3D equilibrium is achieved in case of model of a globe?
Please come again. How the 2D?
How 3D equilibrium
Yes.
is achieved in case of model of a globe?
Model of a globe.
Yeah, sir. Yeah, sir.
Globe means a kind of a sphere in his mind, or because the globe means if you are taking a globe, and then if it is suspended, uh, then in what way you are suspending it, whether it is placed on a surface, all those things we have to consider. For example, if you are going to place the sphere on a surface, flat surface, then the weight of that will be acting. That time you don't have to treat that as a 3D object. You can take it as a one-dimensional object also, because it can be treated as a particle also. Though it is a globe, the globe is going to be placed on a surface. and then it is under equilibrium. That means it is not moving. That time the globe can be replaced by its centroid, through which the weight of the globe is going to act in the downward direction. So just opposite to that, you will have the reaction. So it can be treated as a 1D problem. So it is a globe. But on the other hand, if you are, it is going to be experiencing some other force which is not aligned along the same direction, then it can be treated as a 2D or 3D, depending upon the problem we can take it. The simple example could be a ladder which is propped against a wall, no, that can be treated as a 2D problem actually. But if the same ladder is kept vertically upward, then it will can be treated as a 1D problem. If the ladder, instead of keeping it on, it is such that its surface is touching on a like a side wall, but it is actually inclined, then it should be treated as a 3D problem also. So depending upon the situation we will be having. So from the given input, what I understand is how to treat a globe as a 3D means you don't take it as such, but depending upon the forces acting on that, depending upon what type of forces, that is a two-dimensional force or three-dimensional force, we have to take. The force as such, if the truss member also, it can be a 3D truss, but if you are taking only one truss, one member of that, still it can be treated as a axial force. It can be a one-dimensional problem. Is that clear, or should I explain?
Clear, sir. Clear, sir. Clear, sir.
Are you
Thank you, sir.
convinced? Yeah, thank you. Next.
The next question from Yasin.
Yeah.
Sir, is there any relation between friction and wear?
Yes, it is very much there, because the friction is the culprit in reducing the power transmission. That's why we go for the bearings and then lubrication. In so many applications, we see that our intention is to reduce the friction so that we'll be able to reduce the power loss. Because whenever we give the power, no, it should be transferred as much as possible with less power being wasted in overcoming the friction. So even we are having the bearing, no, and like automobile, you take the like buses, the transport buses, what we operate, which play on the roads, no, every day at the end of the day they are taken to the depot, and then the greasing will be done for the axles, and then other places, friction, the springs also, because we need to reduce the friction so that we can overcome. But there are places where the friction is very important. For example, when we transfer the power from one pulley to another pulley with the help of the belt drive, we need friction, because more coefficient of friction means less slippage, and then less loss, slippage loss. So more power will be transferred. There we should not decrease the coefficient of friction. Similarly, sometimes we happen to see that even a learned person using lubricating the screw jack. So what will happen if you lubricate the screw jack? The coefficient of friction will be less immediately. Like the self-locking condition will be lost. It may be useful to overcome the friction while lifting the vehicle, but what will happen is it may be dangerous to lower the vehicle. So we have to be very, very careful. We should not lubricate it too much. So in general, friction is responsible for wear, but depending upon the need, we have to make a decision whether we have to eliminate or minimize the friction, or we have to increase the friction. Yeah. Next one.
Thank you, sir.
Thank you.
The next question from Madhavan.
Yeah.
Sir, can moment of inertia can also be termed as moment of force or second moment of area?
Please come again. Moment of inertia can also be called as second moment of.
Second moment of area or moment of force.
Actually, the second moment of force we cannot say, because here the force term is not at all there. When a force is acting at a particular distance from the point of our interest, then we find out at what distance the force is acting. That is called the arm length. Then we take that distance r times the force. So that will give us the moment of that force. That is called, in vector form, it is called r cross f. So that is the moment of a force, but instead of that force we have area. So at what distance that area is located from that axis is called the first moment of that area. So here r cross a, otherwise simply r times dA, the infinitesimal element. In case of a whole thing, then the total, then we should not say that, but we can say that integral of x dA is the first moment of area about the y-axis. So here we should not say this is the first moment of force. We have to say it as a first moment of area. Again, if you put one more moment of that, then again we multiply with x, then it becomes integral of x square dA. Then it becomes second moment of area. So force is not coming. Why? That because this is a geometric property. So here it doesn't matter whether you use aluminum or whether you use steel, whether you use some other material to make the geometry. That's why you would have noticed that in the first moment of area or in the second moment of area, the material property are not at all coming into picture. That's why they are called a geometric property. That's why we should not call it as a first moment of force or second moment of force. We have to call it as first moment of area or second moment of area. In case of mass moment of inertia also, we are not bringing that. It will be integral of x squared dm or integral of r squared dm. Actually, this is a mass, no? So integral of r squared dm we can take. If it is a slab, then kind of thing, integral of x squared dm also we can say, no problem. So it is a geometric property that radius of gyration, first moment of area, second moment of area, product of inertia, all those things are area property. Yeah. Next one.
Next question is there.
Thank you, sir.
Yeah.
Sir, can you compare and explain the difference between friction and viscosity?
Yeah, viscosity is also a kind of friction only. We see that in fluid mechanics you would have learned it. But in the same old experiment also we are using it. They are closely related with that. But for materials, metal to metal contact, we call it as friction, and then that is a different study. For viscosity, that is the friction between the fluid and the surface, or within them also. Then we call it as a viscosity. So solid to solid interaction, yeah, we have here this friction, and when the fluid is involved, maybe liquid or gas, whatever be the thing, then we go for viscosity, primarily for liquids.
Yes, sir. Thank you. Thank you so much, sir.
Yeah. Yes. Any other question?
Yes, sir. I hope there is no other questions.
Yeah.
So we will.
Yeah, so you can ask the participants, sir, if there is anything last question they can ask, and then we can wind up.
Participant, if anybody is interested to ask questions, you can come online and you can clarify your doubts with sir. Please come. Okay, sir. Can you switch on your video, sir? Is it possible?
Yes, sir. Yeah. And it is good to see some participants. My old friends are also there because long before I met some of my
yes,
friends. Yes.
Great to hear, sir. And luckily, he got very good connection also. Immediately, he has come online as soon as
Yes,
I was
yes, sir.
given the permission.
Yes, sir.
And
why I'm not able to open the video? I'm just trying to find out.
yeah, please, sir. Please, sir.
Okay, it says the connection seems low
It's
at the
slow.
moment, so you are on audio only mode. As soon as your connection goes back to normal, the video feed
Okay,
will be
let us go.
reactivated. Okay, sir. Then I think now I think it is coming.
Yeah. Yes, sir. Sir, first of all, Actually, we got participants from all over India, not only from India. We got 5 international participants also.
Oh, wonderful, sir. Wonderful. But I'm happy.
Participant.
I'm happy to see, because I know that some of my own friends, also
Yes, sir.
participated. So probably they wanted to see my face. That's why they are here, because
Yes,
already
sir. Yes, sir.
they are expert in that field. So I'm very happy to be here. Yes, sir. One second, I
Good to
just
hear, sir.
turn on the video also. Yeah.
Please, sir. Please, sir. Please.
Yes.
Yes, sir. Good, sir. Good, sir. It's
Yeah.
good to see.
Yes.
And yes, sir. So we got 2 international participants from what we call Vietnam, 2 from
Okay.
Indonesia, and
Okay.
1
Nice
from
to hear
Taiwan.
that.
Yes, sir. Taiwan.
Oh.
Totally,
Okay.
we got 300 participants, and it is
Oh,
very good.
that's
Actually,
good number.
if you
Really
arrange
happy
in,
to hear that.
yes, sir. It is even if you arrange in face-to-face mode, also only 50 or 60 we can accommodate. So I hope this
Okay.
300 people might have got some knowledge enhancement because of this entire session. Because the presentation what you have made is very excellent. The way in which you have brought the session also very nice to hear. Even the layman can understand. So like that.
Okay.
So sometimes actually I got good feedback even during the session also. I got call from
Okay.
my friends and they have given very good feedback. And it's
Okay.
very happy to see you, sir. It's a wonderful
Yes,
occasion.
sir. It's my pleasure. That thank you for giving me the opportunity to take part. And if the participants has got some benefit, I'm happy. And if
Yes,
they
sir.
are having any doubt also, some more doubts also, I'm happy to clarify. You can share my mobile, not the mobile number, the mail,
So, maybe,
because my
yes, sir.
mobile is personal, and the mail ID, so that if possible, if time permits, I'll be happy to help them.
Yes,
Yeah.
sir. Yes, sir. Actually,
Okay.
certainly this will enhance their knowledge and this will help them to go for a better classroom teaching. So
Yes.
even though they might have got some knowledge, this might have enhanced their further understanding and will help them to go for a better classroom teaching. In turn,
Sure.
the students may can get a better idea. And thank you
Yeah.
so much, on behalf of Chennai Technology. And we are also welcome to have more collaboration with you on behalf of Chennai Technology. And thank you so much, sir. We will meet in some other
Yes, sir.
occasions, sir.
Yes,
Thank
sir.
you, sir.
Thank you. Thank you for giving me the opportunity. And then thank you. And thank you, Swapna, for facilitating this. By two
Thank you.
participants.
Thank you.
Yeah.
Thank you. Bye, sir. Bye, sir. Swapna, thank you so much. Thank you so much. We will meet in some other occasion. Swapna. Thank you. And participant, thank you so much. I hope certainly this is a very amazing session. And actually, he has presented in a nice way. And the presentation, they prepare the presentation also in a very well manner. Okay. So I hope this might be a very one of the great session. And thank you so much for being with us. And the next session will start by 2 o'clock. The section is very also very important one. So he, Dr. VB, shortly known he's Dr. V. Balasubramanian, shortly known as VB. He's one of the living legend in welding. So he is going to talk about material science. So that will be very one of the amazing session. So please join by at least 1:50, and so the session will be started by 2 o'clock. And as I said, so evening we'll have also quiz session. And the one of the beauty of this wonderful FTP is even though we have fixed sessions 1.5 hours, so most of the speakers have spent their valuable time up to 2 or 2:30 hours. So certainly this is making our FTP is more worthy and is wonderful. So again, I'm repeating. So only few of you have not filled your forms for getting the certificates. Please do it within today, which will help us to go for preparing certificate. Since, as I said, the certificate will be unique. We have to embed your photographs and we have to create unique ID and we have to give unique barcode, which may help any accreditation agency to verify the certificate in future. So because of that, please otherwise we do not I can prepare the certificate and we can prepare the certificate within a day, but this will take another at least will take minimum 3 days to prepare the certificate. So please, those who are not filled, please give it now itself and you fill the form. And those who have not joined the WhatsApp group till now, please join again. And on this occasion, I also wanted to remind, so on behalf of Chennai Institute of Technology, Department of Mechanical Engineering is going to, already we have announced 2 days international conference on materials and materials application, materials and materials applications. So all the accepted and presented papers will be published in IOP, Institute of Physics conference proceeding, which is indexed in both Scopus and Web of Science. So mostly this conference has been scheduled to happen on September 25th and 26th. Hope the corona will be over by this time. However, so we have planned to conduct the conference only in the online mode. So there, the fact people will be feeling comfortable since it is going to be happen in online mode. So those who want, so you can submit your papers. So I almost I think I have shared my the poster and the brochure. So those who are not got also, you can approach me, and you can forward to your friends also, because your friends also may be very much interested to participate in the conference, so which will help them to come again or to present the papers. And certainly I say all the accepted and presented papers will be published in IOP conference proceeding. The cost also, including the conference cost, only 6,000 is the fees. So only within which everything is accommodated. So no, it's a very less fees, and so you can go for publishing your papers. And thank you so much. So we will meet in the afternoon session. Thank you.